In this lesson, we're gonna focus on torsion. Now, torsion refers to the twisting or rotational deformation experienced by an object when it is subjected to a torque or twisting force. Now, this force causes the object to rotate around its axis, and then torsion is commonly observed in materials like metal rods, shafts, or wires when they are twisted by an applied torque. In engineering and physics, understanding torsion is essential for designing structures that can withstand twisting forces without experiencing excessive deformation or failure. And so let's just define some terms. Torsion is the twisting or rotational deformation experienced by an object. And then torque is the moment that tends to cause twisting. And then torsion is common in transmission shafts in which power is transmitted by rotation. And so consider the drive shaft and axles used to transmit power from the engine of a car. Let's try to connect this wheel. And let's say that these wheels will rotate. And then let's say we have a shaft here, and this is the engine of the car. If the wheels will turn, the shafts will now be subjected to torques because we have these twisting moments in order to maintain equilibrium. And then also consider the shafts built to transmit wind power obtained from the blades of this wind turbine to the generator. Let's take a closer look, and then let's try to reveal what's inside. We'll be able to see this. These are the shafts, and then from the turbine, it will transmit power to the generator. And so these are some real-life applications of torsion. However, in this discussion, we'll focus on the torsion in circular bars. Now consider an example wherein we'll apply a torque to a circular bar. Let's say we have this, and then we'll apply a twisting moment. Notice that this twisting moment will cause the bar to deform. Now, to better understand this, let's try to model it in Blender. Now, for circular bars, an interesting property that we can see is that the individual cross-sections of the bar are not distorted by the twisting, because we can actually imagine that the bar is made up of infinite individual discs which only rotate relative to each other. And so we can imagine this as a combination of these disc cross-sections. Put them together, you can form your bar. And then again, these individual discs will rotate relative to each other, but they will not deform. Now, to better understand this, let's try to model this in Blender. Let's open up Blender, and then let's go to General, and then let's try to model our bars. First, let's start with the circular one. And so we'll press Shift A, and then go to Mesh. Let's pick Cylinder, and then we'll rotate this about the x-axis so that it will be horizontal. So let's change this to 90, and then press S in order to scale the object. Now, since we want to stretch this longitudinally, let's press Y so that we can pull it along the green direction because it's the Y-axis. Press Y and it will lock onto that axis. So we will extend this. This is now our circular bar. And so what we can do next is we can click on the object and then go to edit mode, and then we can specify the number of cuts. Press loop cut, and then let's make cuts. Considering this cross section, click on it, and then let's make the number of cuts equal to, let's say 30. This should be enough. And so click on this again, and also this one. So we have now subdivided our figure. So let's go back to object mode. And then to twist the object about an axis, we need to add an empty object. So press Shift A, go to Mesh. Now empty, press Sphere, and then it is now located here. By the way, to hide an object, you can press H, and then we can now see our empty. As you can see here, this is our empty object. Now we need this to establish the axis of rotation. And so to bring back the object, just press Alt H, and then to twist this, click on the wrench icon, which stands for modifiers. Press modifiers, and then click on add modifier, and then you will go to deform, and then let's pick simple deform. As you can see here, it will mess up our object. Now this is because the axis of rotation is not about the axis that we want. Now since the y-axis or the green line is the longitudinal axis, we need to rotate this about that axis. So press Y, but as you can notice, it will deform our object. And so what we can do is, we can actually change our origin, and then let's make our empty object as the origin. So press empty. As you can see here, this will now be our figure if we will subject this bar to twisting moments. And so let's just exaggerate the rotation angle. Let's make it 100 so that we will be able to see the relative twisting. Now to better see this, let's click on overlays, press the drop down button, and then we can now see geometry. We can now check the wireframe so that we'll be able to see the mesh lines. And so if you will press that, this is now our figure. And so notice that for the cross section, there will be no significant changes, but there will be twisting relative to each cut. Now this is only true for axisymmetric objects. Now what do you mean by axisymmetric? It is the property of an object being symmetrical around an axis. However, rectangular cross-sections are not axisymmetric, and so torsion will actually cause the warping of the bar cross-section. And so if you are to demonstrate that, let's add another object, press Shift A, go to Mesh, and then let's try to add a cube. And then to move this, just press G to grab. Let's move this here. And then we can scale this about an axis. Let's just say, let's move this along Y. Press S and then Y. And then let's make this rectangular. So press S and then let's pull this along the Z axis. So press Z. This is now our cross section. Now another way to make cuts, instead of going to edit mode and then establishing loop cuts, you can just click on modifiers and then add modifier and then go to generate and then press subdivision surface. Click on simple, and then for the levels, ideally we will use 5, and also for the render, click on the drop down button and then click on apply, and then this is now our cuts. And so press add modifier again and then go to deform and then simple deform, and then let's try to rotate this about the Y axis. And so as you can notice, let's just make this longer so that we can see the deformation, and then let's exaggerate the angle of twist. Let's make it 50. This is what happens to our bar. And so this is what we call warping. Now since the warping of cross sections will be very complicated, let's just actually focus on circular shafts. Now if you want to animate this, you can go to animation and then you can click the object. Once you press the object, you can press I to add a keyframe, and then you can pick any of these. And so for this one, let's pick location, rotation, scale, and custom properties. And then let's go to the modifiers, and then you need to check this so that the angle of twist will be added as a property. And so let's start from 0 and then click on this and then have this checked. And then for the next keyframe, press I and then click on this. And then let's now change the angle of twist. Let's make it 100. And then click on this. This is now our second keyframe. And so what's going to happen between this interval will be the actual twisting of the object. And so let's zoom in and then let's play the animation, press space. We can now see the deformation. Now again, this is what will happen due to twisting. Now if you want to slow down the animation, you can move this a couple of frames further. Just click on it and then drag. And then we can now see the rotation that will happen. And so let's go back to the layout and then let's just make this, let's say 40. And then let's now export this object. And then we will save this as an object. So again, export and then press wavefront. And then let's go to downloads. Let's make this the cylinder subjected to torsion. And then press export wavefront object. And then we can now export this file. So again, insert 3D models, this device, and then let's click on this. And so let's rotate our figure, and so we can now actually draw lines. Now initially, this is the configuration of our bar because it is not yet twisted. And so let's screenshot this object, let's copy it here, and then let's try to make sense of this. Now initially, let's say this is the center of the circle. Now if we will draw a horizontal line from this point up to here, then this is our initial figure. Let's also make this red. And then let's say that we have a support on the other end. Let's add some depth. Go to shape format, right click, and then format shape. Click on this, and then let's go to 3D format. And so let's set the depth to, let's say 20, and then let's rotate the figure. So go to 3D rotation, and then let's rotate this about the x-axis here and a bit about the y-axis. Now just assume that this also has a support, and then let's try to name this point as, let's say this is point A. Let's just use another color. Let's say this is point A and this is point B, and then let's try to see how the line will deform between these points. When we apply the twisting moment to the bar, it has now rotated this way. And so again, this is our initial figure, while this is our final figure. Let's just change this. This is our initial figure. We don't have any rotations yet. And so let's identify the center, and then this is our line, and then let's connect this here. So let's say this is point B and this is point A, and then in our second figure, when the torque was applied, we have this twisting moment. And so let's say that from this point, our point B has rotated up to this point. And so let's say this is the new location of B, which we'll label as B prime, and then this was, let's say, the initial point. We can actually draw a line from our initial point. And so this is, let's say, point A. This is the center of the circle, and then we can connect a line here. However, since the new location of B is already here, then we can also draw another line there. This is now our new location of B. And so this angle will be, let's label this as theta. This is now what we call the angle of twist, because from this point, the new location of B is now here. And so let's also draw a line here. And so again, this is our angle of rotation. And then our formula for that will be the angle of twist is equal to TL over JG. Now this is the angle of twist, wherein T is the torque or twisting moment, L is the length of the shaft or bar, J is the polar moment of inertia, and G is the shear modulus, or this is also the modulus of rigidity. Now a mnemonic for this is, notice that this looks like an I, and so you can say that I can see true love in Jesus, who is God. However, my teacher when I was still in undergrad told us that to memorize this is tender juicy, and then lami gid. That's also another way. And then what's famous in review centers is si Tita ang true love ni Jano Gibbs. Now you can use any mnemonic you like. It just depends on your retention. And so let's move this. This is our first equation. And then for the next one, we'll try to develop the formulas. Now let's consider a point here. Let's try to draw this line. And then let's copy this. Notice that if we will zoom in, we can actually see a rectangular section right here. This one. This is essentially a rectangular section. And so if this is point A, point B, we already used A and B. So let's just make this point C, point D, point E, and point F. And so zooming into this element, we have C, D, E, and F. Now, this is a rectangular section, and then since we already discussed that rectangular sections are not axisymmetrical, then this means that this will be subjected to deformation if we will consider these small elements. And so what's going to happen here is, if we will look at the new element that corresponds to this one, then that will be this figure. Let's try to zoom in. Let's try to consider the same point. Let's copy this. Now notice here that for the same slice, this is now our figure. Let's cut it right here. We now have this section. And so notice that this isn't rectangular anymore. And so if we will zoom into the section, it will now take this form. And so let's say this is, again, C, D, E, and F. And so this is what's going to happen. Initially, we had a rectangular figure, but once there is a shearing strain, then this will move slightly up. This is now the new point, and then it will also deform here. And so this is essentially the new element. This has a deformation here and also here, which is equal in magnitude. And so let's try to develop the equation for our shearing strain. And so let's say that this is the shear strain gamma. This is our symbol. And then let's remember the property wherein for very small angles, since the rotation is usually a very small angle, then tangent theta will just be approximately equal to theta. So we have gamma is equal to tangent of gamma. Now to demonstrate this, since the angle here is usually in radians, let's use our calculators and then press shift setup and then pick radians. If you will use tan of a very small angle, let's say 0.00002, that will give you the same value. And so this is what this means. And so since we know this, we can now use trigonometry to derive an equation for this expression. Now essentially, this is an arc length with a central angle of theta. However, since this is only an exaggerated figure, since the rotations are very small, then we can treat this as a triangle. Now let's say this is again point B, and then we will consider this as a triangle. So we have, let's redraw that. This is B, B prime, and this is point A, while this is gamma. And so gamma, or tangent of gamma, will be equal to the opposite side over the adjacent side. Now if this is our reference angle, then this is our opposite side. So this is, let's say, B, B prime for this line, line segment, divided by the adjacent side, which is AB. So this is AB. Now by the way, I gave you this formula earlier, TL over GG. So the length of the shaft is actually this length, from here up to here. This is our L. Let's make this parallel. And so notice now that since AB is just a horizontal line, then this is equivalent to our length L. And so now we can say that the shear strain is equal to BB prime divided by L. So again, these are equal, L and AB. So now we'll figure out what BB prime is. And so if you will try to check the figure, BB prime is an arc length with this central angle. Now we know that in terms of radians, the formula for S, let's say this is the arc length, that will be R, or the radius, multiplied by theta. Now this is in radians. And so this will now be R theta divided by L. And so our formula for gamma will be R theta divided by L. This is now our second equation. And so let's move this. Now this equation that we have derived is actually only an equation for the shear strain along the surface of the bar. Now what about on the inside? Now we will consider the concept that the shear strain increases linearly with the distance from the center. And so let's say that the distance from the center at any point is rho. Let's say this is rho. And then this will be at any point. It can be here, here, or at the tip. This is our radial distance. Now what is the meaning of this? From this linear relationship, since the shear strain increases linearly with the distance from the center, which is, for the sake of discussion, let's just use, instead of R, let's use rho, this one, the radial distance, then the maximum shear will also occur at the farthest point from the center. And so that's why our maximum shearing stress is located here at the farthest point from the center. And so let's now try to derive a formula that will define our stress. Let's redraw our section. We have a circular section subjected to a torque T. This is our center. Now, we can actually consider a differential area within our cross section. And so that area will be, let's say we have this. This is our differential area. So this area will be equal to dA. Again, this is the differential area. And then this differential area is, let's say, located at a distance rho from the center, this radial distance. So if this is rho, then we can now formulate an equilibrium equation. Let's define the force acting on this element. Now the internal force acting on this differential area is equal to the area dA multiplied by the shear stress. Again, this is from our equation that force is equal to stress multiplied by the area. And so let's color our force orange. And so the force acting on the differential area will be equal to the shear stress multiplied by dA. Now, considering the figure, we can now formulate the equation in calculating the shear stress. Now, our condition here is that the summation of all moments caused by the internal forces acting on all of the elements within the cross-section must be equal to the applied torque T, because this will maintain equilibrium. And so essentially, what's gonna happen is we will consider a differential area here, which will also have another force. This is right here, right here, right here, and so on, until you can get all the internal forces. And so since we are interested in combining differential elements, then we need to use integration. And so to represent our equation, we have the torque T is equal to, now let me just write the condition. Again, this is our condition. And so we now have the torque T is equal to the integral from, this is at point 0, we will actually consider the distance rho. And so for this point, rho is equal to 0. So this is from 0 up to a maximum of the radius, because the farthest distance from the center up to here, that's the radius of the circle. And so this is now from 0 to R. And then we need to take moments about the center. And so that will be taking moments about the center. Considering the differential element, we have the force TdA. Again, for moments, we need the force multiplied by the perpendicular distance. And so this is now the shear stress multiplied by dA multiplied by the moment arm, which is rho. So this is TdA multiplied by rho. Now what we can do here is, since we know that the quantity tau divided by rho is a constant because the shear stress varies linearly with the distance from the center of the cross section, then we can say that tau divided by rho is constant. Again, this is defined by this relationship. And so what we can do here, since for integrals we want to move constants outside, then we can divide tau by rho. However, if we'll divide this by rho, then we'll also need to multiply this expression by rho. What we are essentially doing here is, we will just be multiplying by 1, but this will be rho divided by rho. This won't change our equation, but multiplying this expression will simplify our integral. And so let's copy this. This will now be the torque is equal to the integral from 0 to R, and then this rho will be paired with tau. So this is tau over rho multiplied by dA, and then we have rho times rho, that will be rho squared. So this is p squared, and then since this is a constant according to the linear relationship, then we can move this outside. So this now becomes t is equal to tau divided by rho multiplied by the integral from 0 to r of p squared multiplied by dA. Now this expression, as you can recall from your statics, this defines the polar moment of inertia. The moment of inertia is the integral from the minimum radius, or essentially 0, with an upper limit of the maximum radius with an inside expression of r squared dA. This is the polar moment of inertia. And so if you want to express the maximum shear stress, then this will be tau is equal to the torque multiplied by rho and then divided by J. And so this is now our formula. However, in most books, this is also defined as the maximum shear stress is TR divided by J. This is now our third formula. So again, we have the shear stress or the maximum shearing stress, we have gamma or the shear strain, and we also have the angle of twist. So these are basically the formulas that you need in order to solve problems involving torsion. And so I hope this video helped you.